Okay. Oh, sorry. Again. I would like to introduce you, all our presenters, and the aim and what we'll cover of our symposium. Symposium ID is this number. And chair is me, and presenters are Murat Sukuti and co-authors, Henrietta Gartner and Renzo Pozzo from Italy and Germany, Anastasia Kovaleva, Russia from Moscow, and me. And symposium will focus on the discussion of understanding the brain mechanisms of sensory motor integration. And I will use such abbreviation. And here is the scheme about which I will talk in my talk. And how Nikolai Alexandrovich Bernstein introduced sensory motor integration as a process of receiving sensory information from sensors and or effective information, its interpretation in special centers in the brain, and organization the motor response through a feedback system. It's how our Nikolai Alexandrovich determined sensory motor integration. Before him, and he too published works that told us that also numerous brain structure and sensor feedback are involved in the formation of motor programs or formulas of movement, the activation of motor neurons and formation of executive commands to the muscles is considered to be a common final path, Sherrington told us. And in other words, we can say that the brain manifests itself in movement. The ideas about the muscles as an organ of cognition, of spatial temporal relations of things, and coordinated activity of the forms of feeling and thinking with the motor reaction of the body were developed back in the 9th century by Russian psychologist Ivan Mikhailovich Sechenov. Therefore, the study of motor output can be used to look back from the periphery to the structural organization and functioning of the central nerve systems. So our symposium will cover all aspects of sensory motor integration research, from neuromuscular coupling to central nerve systems control of fine and gross motor movement and its effects on cognition and emotional functions. The aim of our symposium is applications of neurophysiological predictor of optimal sensory motor executive functions in modeling the brain-computer interface in neurofeedback training technology, and we will see it. The next presenter will be Murat Sukuti and his co-authors from Department of Physical Education and Sports Education in Marmara University of Istanbul and Bogaji University Biomedical Engineering Institute and Simplana GmbH from Turkey. And their main result is that intermediary rhythm at 0.15 hertz in facial skin microcirculation or earlobe is associated with the subjective experience of profound mental relaxation. It must be very interesting and exciting results. After him, Henrietta Gartner and Renzo Pozzo from Italy and Germany will retold us about that musical training being multisensory in nature provides a beneficial and rewarding ground for cognitive training programs. And after that, Anastasia Kovaleva will retell us about such physiological parameters as bracing, amplitude, heart rate standard deviation, high alpha power, and theta power could predict inter-tap intervals variance for 40 beat per minute rhythm. And finally, my presentation will review studies suggesting that upright posture and balance are predominantly controlled by neural circuits considering the key role of alpha oscillations in sensorimotor integrations. And so I will wish success for our symposium, and we can start.
Okay, thank you, Dr. Bozanova, for having our study in your symposium. I hope we will meet you all in face-to-face symposiums in the future. So our study consisted of a combination of two series of experiments. So thanks to my colleagues for their great contributions to these experiments. I would like to start this presentation by briefly talking about the autonomic nervous system. The autonomic nervous system has been studied for years to define with physiological parameters. It is conceptualized as a duo, the sympathetic and parasympathetic nervous systems. Autonomic nervous system contains central organization of the reciprocally coordinated neuronal functional loops, and also the peripheral effectors producing the sympathetic and parasympathetic antagonistic states. Enhancement of sympathetic drive and the concomitant physiological processes forms the stress response. However, this antagonistic state, so-called relaxation response, characterized by parasympathetic dominance, has escaped a strict physiological definition. Heart rate variability has been employed extensively for this purpose, but some physiological constructs on HRV, such as sympathovagal balance, these have been proven independently to be misleading or even false in some cases. So cardiovascular rhythm analyses are widely used to detect these antagonistic states, parasympathetic and sympathetic states. Low frequency and high frequency are the conventional frequency bands of the cardiovascular rhythm analysis. Low frequency is mostly associated with the sympathetic response, and the spectrum of this band is between 0.04 to 0.15 Hertz, or sometimes they use it 0.04 to 0.12 Hertz. But after the European Task Force on 1996, low frequency band mostly used as 0.04 to 0.15 Hertz. Low frequency rhythm is affected by both baroreflex and some slow respiratory oscillations. Besides that, the other conventional frequency band is a high frequency band, which range is between 0.15 to 0.4 Hertz. It is mostly associated with parasympathetic response, and the spectrum of it, as I say, 0.15 to 0.4 Hertz. It's affected by respiration directly, and this high frequency band also known as the respiratory band. There are three rhythms inherent in circulation, actually. The first one is baroreflex rhythm, which usually centered at 0.1 Hertz. It is thought to occur due to 10 seconds of impulse transmission in the parareceptor cycle. And the other rhythm is respiratory rhythm, which is usually, again, centered at 0.25 Hertz. The presence of the respiration rhythm in the circulation occurs due to direct activation of respiratory neurons, actually, and mechanical effects of breathing, the change in the thoracic blood filling, causes this rhythm. And we have a third rhythm, which is called intermediate rhythm, centered at 0.15 Hertz. It's different from these two rhythms. The intermediate rhythm was first found in skin blood circulation. Also, it's thought that the source is brainstem for this rhythm. You can see a full cycle of forehead blood circulation here. Red and yellow color represents there is more blood under the skin, and the blue color represents there is less blood under the skin. Now here you can see the frequency analysis of 3 different physiological data of the same person, and these data collected simultaneously. As you can see in these graphs, the arterial blood pressure data's time frequency distribution shows us that 0.1 Hertz rhythm continuously uninterrupted. The data which is collected from the left earlobe PPG data shows us that there is a frequency peaked at 0.15 Hertz, actually, which is intermediate rhythm. And from the respiration data, which is collected from thorax movements, and its frequency analysis shows us that it has peaked at 0.2 Hertz. Probably this person breathes a little bit slowly than the normal people. But as you can see here, the intermediate rhythm is different and independent from the baroreflex and respiratory rhythm, which can be seen in PPG data. Let's elaborate this intermediate rhythm a little bit more. The rhythm was first detected in the bloodstream in the forehead skin, actually, at 1987. It has been shown in both human fMRI and invasive animal experiments that this neuronal activity results from the coordinated activity of neurons, which are clustered in the reticular formation of the brainstem. And it's shown that this intermediate rhythm was different from the baroreflex rhythm. Intermediate rhythm has been shown to attenuate or disappear in situations such as stressful acoustic stimuli, orthostatic load, or induction of somatic pain. So it disappears in arousal times, physiological arousal times. It has also been reported to occur in the earlobe during long relaxation with eyes closed situations. And it has been shown in some parts of the brain, insula, sensorimotor, and parietal part of the brain. That's a new finding, actually. So as I stated at the beginning of the presentation, we conducted 2 series of experiments. The aim of the first experiment was investigate the effects of different types of exercises on the intermediate rhythm. We have 2 types of exercise. First one is harmonic exercise. During harmonic exercise, we have hypothesized that the percentage of total occurrence time of the intermediate rhythm is going to be higher than the other circulation rhythms in the PPG data. And during the agonistic exercise, the percentage of total occurrence time will decrease. So that these 2 were our hypotheses. On the second experiment, as Furtscheller has pointed through fMRI that the intermediate rhythm is observed in the human brainstem, the aim of our experiment was to investigate the resting state brainstem fMRI rhythms of sedentary and physically active people. So, In the first experiment, there were 9 male participants whose ages vary between 22 to 41 years old. They exercised on a bicycle ergometer in an eyes closed and mentally relaxed state. Participants started harmonic exercise first. After the completion of harmonic exercise, they continued to agonistic exercise. So there were no rest between these two exercise types. The only rule for the harmonic exercise, the participants instructed as they can do the exercise, whatever the exercise load they want. So the exercise load was self-adjusted, and time to stop the harmonic exercise, again, it was self-adjusted. So they decided when to stop the exercise. The only rule for the harmonic exercise was they should reach the exercise load linearly, but which is determined by them. Besides that, in the harmonic exercise, we asked to participants that they should do this harmonic exercise in an eyes closed and mentally relaxed state. We asked that for them, and the reason behind these instructions was we wanted to observe the intermediary rhythm if it occurs in an exercise, if they try to stay mentally relaxed. After the completion of harmonic exercise, they continued to agonistic exercise, which power output increased steadily until the exhaustion, 5 watts for every 5 seconds. So they did the agonistic exercise until the exhaustion. You can see an example, a graph of power in the y-axis and at the x-axis time. The participant started harmonic exercise. It increased the load until, let's say, 100 watts, and he wanted to stay there. And he wanted to stay like 10 minutes. He exercised at this load. And when he wanted to stop harmonic exercise and continue immediately to agonistic exercise, you see the linear increase of the power until the exhaustion. So what we collect during these exercises, we collect forehead skin vasomotion using photoplethysmography, respiration data from thorax using thorax movements, blood pressure from finger, HRV from chest area, and locomotion data. Percentage of total occurrence time of 3 rhythms, baroreflex rhythm, respiratory rhythm, and intermediary rhythm calculated for each parameter. Here you can see, let's say, for respiration data, the dominant rhythm was, as expected, the respiratory rhythm. The mean is 99%. As expected. The interesting thing is in the PPG data, the dominant rhythm was even in the exercise situations. It was the intermediary rhythm. Actually, these results provide strong evidence that not only the intermediary rhythm has observed in a calm state away from external stimuli, but also we can observe it during physical activity if the person is mentally relaxed or tries to be mentally relaxed. The intermediary rhythm, actually, against our second hypothesis, continues to exist even when the physical load increases, even in the agonistic exercise. Here you can see the time frequency analysis of the data simultaneously collected from different devices during the harmonic exercise of the same person. Here, this is the raw PPG data. This is arterial pressure data and its frequency analysis. You can see the baroreflex rhythm here at 0.1 Hertz. Here, the HRV data's frequency analysis. Again, you can see 0.1 Hertz. Somewhere it is interrupted, but we can call it continuous. And this is a great respiration frequency. We can see it 0.928 Hertz. In the PPG data, which is collected from the forehead, you can see it is at 0.2 Hertz actually, and it's continuous, not interrupted at all. Our results support that the intermediary rhythm is still independent of the baroreceptor reflexes, which is 0.1 Hertz, and the breathing rate, which is 0.29 or 0.3 Hertz in the during the harmonic exercise actually. But the other observation of this experiment was that the intermediary rhythm in the PPG data is shifted from 0.15 Hertz actually to 0.2 Hertz. But still it's independent and different from baroreflex and respiratory rhythms. We observed that only for this person actually. And now you see again same frequency time analysis, but from a different person. For some people, even the baroreflex and respiratory rhythms seems continuous as for this person. The intermediary rhythm is not continuous. It's as you see, the appearance here, 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 and disappearance of the intermediary rhythm. It sometimes appears and sometimes disappears for some people. The second experiment was conducted with 10 sedentary male and 11 physically active male participants. Their ages varied between 21 to 58 years old. We collected resting state, anatomical and functional MRI data for 7 minutes. We performed brainstem segmentation manually. Drawing was performed on approximately 30 slices in anatomical brain magnetic resonance images of each person. So you can see a slice of manually drawn brainstem mask on an anatomical MRI. After that, realignment and rigid registration were applied as standard pre-processing procedures. You can see the slice of functional brainstem mask, which is superimposed on functional MRI. After that, time series of corresponding brainstem voxels for every voxel, time series were calculated. The power values of each voxel was calculated in 4 frequency bands, these 4 frequency bands. The average of the power values in 4 frequency bands, each frequency band in itself, obviously, of all manually segmented voxels, and the average intermediary rhythm to low frequency ratios were calculated in order to compare these two groups. Here you can see a participant who has actually strong intermediary rhythm. You can see the spatial distribution of power values of the intermediary rhythm here in 4 slices of his anatomical MR. And you can see his histograms in the y-axis, number of voxels, and the power values in the x-axis in 4 frequency bands. You can see here he has more voxels, more powerful voxels in intermediary rhythm range, actually. Here we see the relative power of different frequency bands between the 2 groups, sedentary and physically active group. The relative power of the intermediary rhythm in brainstem voxels was significantly higher in the physically active group. There was no significant difference in the very low frequency or high frequency, but there was a significant difference in intermediary frequency. Also, we checked intermediary rhythm to low frequency ratios. You can see that on this graph, the first 11 dots represents the physically active group, and the last 11 dots from here, last 10 dots, sorry, from here to here, represents the sedentary people. As you see in the graph, 6 of 11 participants of the physically active group had a ratio bigger than 1, and only 2 of 10 participants of the sedentary group had a ratio bigger than 1, only 2. The capability to preserve the intermediary rhythm during mentally relaxed physical exercise in forehead skin vasomotion, despite a markedly elevated pressure flow product in the systemic blood circulation, suggests an autonomous neural process being causative in this spatial microcirculation area. For the second experiment, since the participants were in a resting state but without any tasks, we give them no tasks, and we did not conduct any questionnaire after the experiment, actually. The relative power of the rhythms may vary depending on the psychophysiological situation of the participant. If they get any anxiety, probably their intermediary rhythm was affected negatively. Also, the intermediary rhythm may appear in different relative powers and distributions among individuals. The strong presence of the intermediary rhythm in brainstem voxels, especially in physically active subjects, supported by recent finding on the mediating role of the intermediary rhythm in neural processes of interoception in lower, brainstem and or higher central nervous system areas. These findings imply that the rhythm at 0.15 Hz, the intermediate rhythm in facial skin microcirculation, which is associated with the subjective experience of profound mental relaxation, reflects on the peripheral level an order-order transition originating in the reticular formation of the brainstem. Thanks for my co-authors' contributions to this study.
Thank you.
Thank you.
Thank you. Your presentation, maybe it's too long a little bit. And if we have no 21 minutes, maybe you can make it shorter if you would like. It does not matter. A lot of questions I've got, but I think that we will not ask now questions, or we will ask. How do you think?
You are the
I
boss.
think we will try to ask. Maybe so it will be okay. I mean, the timing of our symposium.
Okay. Because it's interesting for me. For example, it's interesting for me. Maybe for others too have some questions, because very interesting presentation from my point of view, and it's just a very new original data Murat and co-authors received. And I was wondering, because I am not specialist in heart rate variability very much, but I saw that spectrum of heart rate amplitudes have individual peaks. And what do you think about individual peak of your very interesting intermediate rhythm? How it's connected with individual state?
Actually, normally the range of intermediary rhythm is 0.12 hertz to 0.18 hertz in without exercise.
And my question was, maybe you noted some connection, interrelations with individual frequency, peak frequency of this rhythm, individual peak frequency, you understood my question, and condition of participants of your subjects. No, you did not know?
No, we didn't.
Okay. If somebody has more questions?
Yes, I do have one, maybe more question, but am I right that if somebody wants to extract this range for individual rhythm, we have to do it manually, because standard software packages for heart rate variability analysis do not provide such range, and is it possible to use it as an indicator of mental stress, maybe mental arousal, because it's a very interesting instrument. If we could connect it to some mental workload, maybe. Am I right? It's the function of this rhythm is something like this.
Yes, actually, you are right. We also thought that this rhythm appears in a mentally relaxed state of the person.
So if it will decrease, it means that the arousal increased.
Yes.
Mental workload increased as well.
Yes, you are right. But this rhythm appears in specific areas, as we found, like in the forehead and in the earlobes. From PPG data. For HRV data, I don't know if it appears or not.
But what do you think about using PPG data to compute HRV spectrum? Some papers said that it is possible to use PPG data to compute the spectrum of heart rate variability, just R intervals like a peaks of PPG.
Yes, they use it as from PPG data. They try to find, as you say, RR intervals. Actually, it from now on it turns into an HRV data. It's not a PPG data, so you should do the signal processing sequences correctly. You should use raw PPG data and noise filter it, and after detrending and other standard preprocessing, you can apply FFT that raw data.
Mhm.
Actually, it
Yes.
was not provided.
Thank you. Thank you very much.
Thank you. And Murat, could you just explain terminology? What does it mean disappear? Rhythm disappear. Amplitude is lowering. And what does it mean disappear?
Amplitude lowers. Another. Yeah.
Excuse me. More questions? Renzo?
Small one. It does. I suppose there is no kind of relationship between endorphin.
I don't know,
because
actually.
It is too small the time elapsed to have effect of endorphin. As far as I know, endorphin comes out when you are going to make a resistance and exercise very longer, 20-30 minutes. But it would be interesting to know if there is correlation between endorphins or not. But very nice presentation. Thank you very much.
Thank you.
Thank you. Okay. And now Renzo time.
Okay, then I give the second print. Now you should have the. Do you see this?
Okay.
Yes, we
very
can.
nice. So, yeah, Olga, thank you for the presentation. We will going to speak about the coordination between pedal and finger forces during piano playing, classical passage, and this with respect to the quality of sound. A small overview about what was done about these topics: complexity of stroke behavior and complexity of pedal behavior. Then some information about the methods, the sensor we used for the forces on the keyboard and on the pedal, sound and video recording, and the quality of sound in form of questionnaire. Then the results, starting with sound quality, and then about the forces, and of course about the relationship between forces and between the time delay between the both kind of forces, which is represent a kind of coordination pattern, and some conclusion, of course. So this is the complexity of the keyboard in a classical piano. So you see there are a lot of mechanical leverage, and when you push down the finger on the keyboard, then the hammer is moving in a ballistic motion, and simultaneously the damper is going up from the string. So the string and then allow it to vibrate and give the sound. Well, this is a very complex, and you see, you know that there are 88 systems of such a system in a normal grand piano. Again, a small overview of the most important phases. When we start, then the damper is this is lying on the string, and we don't touch now the key, and this complete stopped the vibration. So then we begin to start to push down the key, and before the key reach the ground, the dampers begin to move upwards. After this phase, the hammer is moving in a ballistic form. There is no more possibility to control the movement after this phase. So in this phase, the hammer is just before hitting the string, and the damper is still upward from the string. And of course, the string is vibrating and coming the sound. Then the hammer is falling down. So what does it mean in terms of producing sound? In a couple of experiments, this is one of the most interesting, Kinoshita, it was shown how much impulse is needed to elicit a note. And you see that it takes a small force impulse, that is Newton, and after the force is reaching the maximum, then comes the sound, and this moment is correspond to the lowering the touchdown of the of the key. So when the key is down on the ground, then all is over and the sound is coming. So you don't need much more force to produce the sound. Of course, if you made the so-called dynamic in terms of musical, you can play piano, pianissimo, forte, fortissimo. And what does it mean? It means that there is a relationship between the intensity of the sound here in decibel and the force. This kind of relationship is not linear in such a way for the maximal, the peak force, and for the average force. So this is very important. In other words, what does it mean? That we need only an active, so-called effective force. We don't need much more forces after this point. So if one is making this force, this much more impulse, then it could be used as fingering technique, because you are pushing a pivot system from one finger to the other, or it means a non-economical movement pattern. So it means, again, that the brain is making something not economical, not necessary to have the sound modulation. And we call this passive maximal force. Now I give the word to Henriette to explain pedal.
Yes, we are also talking about the pedal. Normally, and the pedal and the user of the pedal. A normal piano had 3 or so 4 pedals, and we are only speaking about the right pedal, which is the sustained function for the sound. You can see here pushing down with the right foot and holding down the right pedal means that all dampers, like Renzo told, are lifted simultaneously and staying up from the strings. And the right pedal, so-called, sometimes called the damper of sustaining pedal, raises all the dampers. Furthermore, the vibration of the strings is also a question cause other strings to vibrate, so that further overtones complement the original tone. The damper pedal thus generates a rich tonal quality. Therefore, like you can see, it's vibrating freely. How to use the pedal is in a different way than to use the key, because you can use the pedal in a differentiated way. Here you can see on the left side that the damper is on the string, so that the toe is off. There is no force on the toe. Then, if you push down the right pedal, you have the maximal force and all the dampers are up, but also we can use the pedal in a gradual way, that we can push down softly, go up softly in a gradual way that makes also the sounds more clear or more dirty, like you want with your ear. So now we can see, but we will hear later in the results, if the pedal force is not going down to 0 Newton, like with the professional pianist, the damper is walking gradually on the string. But in contrast to the students, the dampers are always going down, so that the toe is off, and the dampers is lying totally on the string. Therefore, the professional pianists are able to use the pedal in this gradual way. This can be a clear indication, and that's very important, of the relationship between the differentiated use of finger and pedal, and therefore it is also indicated that the hearing capacity is well tuned with the motor control of finger and pedal. So we are always speaking about the Bluetooth of the system, ear, finger, foot.
Now we had the most important question were, how can the use of pedal influence the quality of the sound? So are difference between professional pianists and students? Which kind of parameters correlate with the quality of sound? And of course, are there some kind of hints for maybe visual feedback of force time curves as supplementary information in order to improve the fine-tuning, this Bluetooth, between the motor control of fingers, pedal, and hearing? This is a method we used. 2-octave force sensor, 2 octaves. working 300 hertz, one microphone and one camera, and then two other pedal sensors, one for the heel and one for the toe. That means the pedal forces. So to differentiate both the contribution of the foot, working 1000 hertz.
Now we are speaking about the methods, the questionnaire of sound quality, because this is always important when we are speaking about the music. We had a jury of 5 highly qualified professional musicians, and the descriptive criteria are the sound balance between the right hand and the left hand, the melody and the accompaniment hand. The legato means the construction of the phrase, this horizontal line. The figures, left hand, stability and sound pattern of these figures. Use of the sustained pedal, if it's in a use, a differentiated, sophisticated, also an intelligent way to use the pedal, and of course the total impression. Therefore, we had an ordinal scale for each criterion from 1 to 4, from very good to by far not so good, that later we could make it with this jury to do very good and good. It was the professional pianists, and not so good, by far not so good, were the students. We also had 13 pianists in total, 4 professional and 9 students. The instrument was a grand piano, and the piece they had to play was the first movement, the first bars, bar number 1 to 5 of the sonata by Baldassare Galuppi, number 5 in C major. And the testing schedules they had to play in the original dynamic 4 repetition in piano, and then 4 repetitions in forte, with the conditions and the target to play. They were asked to play with their best interpretation and constancy, using always the same fingering, pedalization, and the same given tempo. Of course, they had 2 weeks time before to prepare all the piece before the experiment session. This is now the piece. We will hear this played piece, the first 5 bars of this movement. Langsam.
Just a moment. Oh, sorry. Maybe.
Versuchsperson 9, Galuppi im Piano, erste Wiederholung. For synchronization.
Did you hear the sound?
Yes.
Okay, nice. So we concentrated the analysis on the first part here, this note. So first question was to synchronize, and you had at the very beginning that this note was synchronization was done via simultaneous hitting of 1 key on the keyboard and the heel on the sensors of the foot. And you see here an example. The right hand is the melody hand here, and the left hand is the harmony here. These are the notes, and these are the heel force and the pedal force, the toe. So we, according to the interaction, we define effective force, not the maximal force on the key sensors, and a maximal force on the pedal, and of course the time to onset for force on the key and force on the pedal. So this allows us to define the so-called coordinations, time coordinations structure. So we define a time delay of onset forces and a time delay of maximal forces. Now we come out to the results. The first results are referring to the sound quality. And you see that according to the defining criteria, 5 criteria, and according to the scale, the professionals subjects, they got the best scores. No more about 1.5. 1 is the best score. And again, the students, they became 3, or the best one was 2.5. So that was interesting, because the small deviation, standard deviation, means that the jury were, the subjective impression were so-called objective evaluation. Now we come to the results dynamic, and we get the first impression about the forces at per se. So we have the forces on the left hand here and on the right hand here in dynamic piano and dynamic forte. So you see that there is no great difference for the left hand, only this note in piano, that was this note in forte, I'm sorry, but the differences are for the right hand. Remember, the right hand is a melody, and the difference are in terms of absolute value in forte, clear for all the notes, and for some notes also in piano. But one of the most interesting difference is the structure. The pattern of the professional corresponds to the natural way of how music works. This pattern, higher, lower, is exactly what the music needs to be judged as fine, nice music. So, and you see that the students are not able to make this. So the difference between forte and piano is again higher for the professional than for the students. We were interested about the ratio, because the ratio is the combination of the sounds and of the forces is interesting. So we calculated the first quotient. The first ratio was between forte and piano for the left hand and for the right hand. And again, for the left hand means harmony, not great difference between the two groups, and for the melody hand, significant difference for both the groups. This is only forte versus piano. What happened if we compare, make the relationship between right hand and left hand? This is also important because the music needs this. And we made also this kind of quotients. So 5 quotients. And again, the difference are similar to the picture of, we showed before, and it means that the professional, they have this kind of quotients, the ratio, in both piano dynamics and forte, whereby the students were not able to have this differentiation. It means they were really able to differentiate between right hand, left hand, and between the successive coupling of notes. First, second, third, fourth, 5. Third, second, third, fourth, 5. This structure is not random. It is absolute due to the voluntary way the professional are playing. So it reflects then the atom way how the brain is working. Looking now about the reproducibility of the pedal forces, you see how a professional player is able to reproduce exactly the elongation in terms of graduality, and with a small difference in terms of time, but we know there is here 15 seconds. So the structure is the same in piano and forte, and this means again the gradual utilization, whereby the students were not able to do this. And you see the difference in piano. How huge is this difference between forces exerted on the pedal when the damper is all up and totally zero, lying totally on the strings? No differentiation, as no gradual differentiation. Again, this difference is not so great, is not present in the students, but the difference between piano and forte, even if it is small, 10 newtons maybe, it is significant for the professional. So the professional are able to modulate this range of forces differently in piano and in forte. Now looking about the time structure, and as mentioned, I said we defined two kinds of delay: onset and maximal forces. And you see here the 5 combination. For each combination, the first value means onset and the second value means the maximal forces. As you see, the professional, they have all the time positive value. It means the force of the pedal comes later, always later than the force of the keyboards. And these values are significantly higher than for the students. This is in terms of onset. You see here, minus means that sometimes the students anticipate the pedal. And this means a very difference in the quality of sound, as we saw. And this difference are quite significant in terms of statistical. The same pattern is made in forte. Very nice. So the conclusion, pianists, the combined activity between keystroke and pedal utilization represent very fine-tuning coordination of motor control strategies which otherly influence the quality of resulting sound. Yes, while the sound intensity depends mostly by the velocity of keystroke, this is the difference with pedal. A full sound and the resonance effect can be enriched by gradual utilization of the pedal. That means not on-off, but the modulation in between. Professional pianists show a much more fine modulation of peak force and lower force in the pedal than the students. And according to long experience of piano teacher, the differentiation in using the pedal correlates with the differentiation using in the fingers. So the professional pianist activate the pedal later than the student, 200 milliseconds versus 50 milliseconds. And this means that pianists with less differentiation in the fingers are inclined to use the pedal in the same way, namely undifferentiated in piano and in forte. The last conclusion is maybe visual inspection of the forces time curves, keyboard and pedal, can enhance the perception of kinesthetic behavior in order to improve the use of pedal. Limitation of and suggestion of the study is with no multiple session in order to verify rate and limits of improvement via visual kinesthetic feedback, considering other parameters regarding central nervous system as well the autonomic nervous system. That's right. We had this in mind, but we have technical problem and time constraints. No separate methods for tuning the sense of force, a large number of subjects with the same level quality, and follow-up study in several sessions. So this is our knowledge for the firma company Novel, professional pianist, and the student, of course. Thank you very much.
Thank you, Renzo and Henrietta. Very nice, very interesting. And have you tried to use your results in your practice with students, for example, to giving them feedback?
Yes, that was the last conclusion. Yes. You know, you must work with musicians. Musicians are not so predisposed to make this kind of scientific research, but we had tried. We have no standard, no such a follow-up study possibility at now, but we are going, we hope to do this.
Okay, next
Thank you for
time.
this.
Can I say a few words just as a remark and to interpret why did you obtain such results? I think it's all you say it's about automatization of the finger movements, and as a result, in professionals, they could automatize their movements faster, so it leads to release of the working memory capacity, for example, and other resources. They could not to control consciously all their movements. They could direct their attention to the impression and different emotional expressions. So maybe it's about this thing, because of course they and students and professionals, they play piano, but students have to control consciously. I think it's about this.
Thank you for this question, Anastasia. I personally, I was very interested to use EEG. EEG. I'm not a specialist, but I suppose that with EEG we can get information about which kind of working memory and so on. Yes.
Yeah.
And of course,
Thank you.
for students or for pianists when they started, or not so much professional, but also in the professionals, it's always the problem that pianists don't listen themselves. And using this fine tuning in the fingers, using this fine tuning in the pedal, you can't control so much. You can only control with your ear. So you must develop the how the sound has to be, and then to make clear and these fine things. It's a long way.
Also, the application of heart rate variability would be interesting, because if you know that we have some kind of relationship as Murat showed, it will be very interesting, because it means that professionals are relaxed.
Yes.
I was impressed of the presentation of Murat that for this way. Thank you.
Thank you.
Thank you.
Thank you. And Anastasia, it's your time.
Just a minute. I will start the demonstration. Wait, it's not mine. Where is mine? Just нет, это не то. Где моя? Вот она. Так. Here we are. So, dear colleagues, I would like to say thanks to Olga and Murat for organizing this symposium and to inviting me. And of course, it's very sad that we could not meet each other face to face, but just looking for it. And today I will present the results of our research of physiological predictors of audiomotor synchronization ability in adults. So audiomotor synchronization is a part of the sensorimotor integration, as Olga presented in the first part, and such a concept as timing. It is a fundamental characteristic for children, for adults and elderly people, both healthy ones and patients with different sensory and cognitive and motor disabilities. In most cases, no matter clinical, sports, young or adult, everyone desires to enhance their performance in different kind of activities. The well-known Yerkes-Dodson law dictates that performance increases with physiological or mental arousal, but only up to a point. When level of arousal becomes too high, performance decreases. Moreover, the optimal level of arousal when performance is maximal depends on the task difficulty. The more complicated tasks require less arousal. So we can apply common physiological indicators to predict task performance. We applied synchronized tapping tasks as a model of sensorimotor performance. And I'd like to note that optimal performance in different manifestations has physiological correlates. It's a relaxation of the muscles that are not involved in the tasks, facial muscles usually, changes in brain activity, for example, alpha power increase, breathing patterns, and heart rate variability shifts. But there are a small number of studies where associations between physiological indices and tapping performance were described. So sensorimotor synchronization and timing abilities and rhythmic behaviors do not exist in vacuum, of course. It is typically embedded in social context. For example, in the picture, you can see some examples. One is when one bird is singing solo, and while another one is listening and evaluating it as a potential mate, maybe. The second one is synchronized waving in crowds, and finally the timing of human conversation turn talking. Of course, our emotional states resulted in HRV spectrum and heart rate variability pattern changes, and sensorimotor synchronization is associated with executive functions. First of all, it concerns long intervals perception and reproduction, so-called suprasecond intervals. Such tasks require working memory, anticipation, and attention resources. At last, self-regulation. It includes different aspects of cognitive, physiological, and sensorimotor functions. All these branches are interconnected and can influence each other. So the study aimed to reveal physiological indicators of the sensorimotor synchronization performance in the model of sub-second and suprasecond intervals production, based tapping according to the metronome auditory cues. 52 healthy volunteers participated in the research. Audiomotor synchronization was tested with synchronic rhythmic tasks when participants had to tap their dominant hand on a sensory surface in synchrony with the metronome sounds. I mean, the isochronous rhythm of a given frequency. Before the start of the session, background physiological parameters were recorded, and the same parameters were recorded during the task execution as well to monitor participants' arousal and stress level. Rhythm maintenance was assessed as an intertap intervals variance. It means the stability of the internal rhythm patterns, and rhythm accuracy as a mean error. I mean the difference between participants' time tap and stimulus onset. And here we will present results for rhythm maintenance only for variance of the intertap intervals. Here you can see the record of the tapping task where the green dots on line, I'm not sure that you clearly can see, the green dots and green line represent interstimulus intervals between metronome sounds, and the red dots on line reflects intertap intervals of the participant. So we choose quite a wide range of frequencies for sensorimotor tests, from 30 to 180 beats per minute. And such choice was based on the recommended parameters and the fact that short and long intervals, perception and reproduction engage different neural mechanisms. Short intervals have a period of less than 1 second, more than 60 beats per minute. And long intervals have a period more than 1 second. That's so-called slow rhythms, 30 and 40 beats per minute in our design, experimental design. As physiological indicators, we used one-channel EEG, photoplethysmogram, skin conductance, breathing rate and amplitude, and forehead muscles tension, EMG. So let's go to the results. First of all, a brief description of intertap intervals variance of different rhythm maintenance. Here you can see the pronounced decrease of variance with the metronome and tapping frequency increase, but only up to a point of 60 and 90 beats per minute. Then with a faster tempo, variance became higher again. Here we, I think here we face an interesting issue concerning sub-second and suprasecond intervals, perception and reproduction described above. Many authors argued that long intervals, slow rhythms are much more difficult to maintain. And such tasks involve the prefrontal cortex, cognitive functions, and conscious control in general. Whereas short intervals, fast rhythms, are considered as more automatic motor action. The next two slides will show the dynamics of some physiological parameters during sensorimotor synchronization with different frequencies. I purposely put on the one screen two types of graphs for one parameter, heart rate. On the left, you can see the mean value only, and on the right, the mean with confidence intervals. Here we're dealing with the great inter-individual fluctuations, standard deviations, confidence intervals, so we obtained no significant differences between tasks and physiological parameters, unfortunately. But on the left, you can see increase during the fastest tempo in heart rate. And just a remark that all tasks were randomly presented. So usually 180 beats per minute was executed in the middle of the session somewhere, not the last one. The example of two physiological values, heart rate on this slide and forehead EMG on the next slide, demonstrated such dispersion which levels out all group differences. This is the dynamics of forehead EMG, but we similarly muscles tension reflects intertap intervals frequency. I mean, EMG amplitude increase with the rhythm frequency, but not significantly again due to great dispersion. Finally, to the sensorimotor ability and physiological indicators relations. We applied multiple regression analysis to predict variance with the physiological characteristics as independent variables. If we'll take the physiological parameters during the task execution as independent variables, we get the following predictors for intertap interval variance of different rhythms. There were no predictors for 30, 60, and 180 beats per minute tasks. And forehead muscles, skin conductance with the positive coefficients for the 40 beats per minute, and standard deviation of normal to normal heart rate intervals, SDNN, with negative coefficients for the 90 and 120 beats per minute. As to SDNN, it's a measure of heart rate variability, one of the indicators of heart rate variability. So we see here that heart rate variability is associated with low intertap interval variance, I mean with better sensorimotor performance. As to 40 beats per minute prediction, here we see that low muscle tension combined with low skin conductance, low sympathetic activation and emotional induction suggest low intertap interval variance, which means good sensorimotor performance again. We also took resting state physiological parameters as independent variables in the regression equation of all rhythmic tasks. We got the significant negative association between resting state alpha peak frequency and 30 and 180, 180 intertap interval variance. The higher alpha peak frequency at rest, the better performance, lower variance during the sensorimotor synchronization task participant will demonstrate. It is interesting to note that both of these tasks, 30 beats per minute and 180 beats per minute, had no real-time physiological predictors. Moreover, these rhythms were the most difficult to maintain in regular intervals. So what should we think about this and other results of the study? We suppose that in the most complicated tasks, sensorimotor synchronization ability is determined by so-called endophenotypic features as EEG, specifically the resting state alpha rhythm frequency, and does not depend on the current arousal level during the task execution. Maybe it's just a speculation. And at the same time, optimal performance in the model of sensorimotor synchronization with other frequencies requires specific reorganization of functional systems of the body. I mean, low forehead muscle tension, low skin conductance, and high HRV simultaneously. There are some papers where the role of such reorganization in musicians and athletes is emphasized. We did not observe alpha power correlations because I just want to comment the introduction of order, because in my abstract I mentioned the alpha and theta power significance in these tasks, but later I added my sample and added some other subjects to analysis, much more than in the first time. So the regression analysis and the predictors changes dramatically. So finally, we did not observe alpha power correlations, but found out that irrelevant muscles relaxation is critical, really critical for optimal performance in some tasks. And to summarize the results, I'd like to conclude that the easiest rhythms to maintain is 60 and 90 beats per minute, and long intervals of slow rhythms reproduced with the highest variance. So we observed great individual variability in physiological parameters during sensorimotor performance. And sensorimotor synchronization with the rhythmic sounds of varying frequency can be predicted with the resting state and recorded in real-time physiological parameters, but of course future research is needed to find out predictors for rhythm accuracy, rhythm reproduction accuracy, and to design some interventions, maybe biofeedback or neurofeedback for sensorimotor ability improvement through self-regulation training in future, of course. So thank you for your attention.
Thank you, Anastasia. Some questions, Murat, Renzo?
Actually, I have one question, maybe two. You use SDNN as HRV parameter, right? Only SDNN, or?
I understood your question. The fact is that we, of course, we applied a HRV spectral analysis, but the task duration was too short to use LF or HF or other frequency domain parameters. So I just use such of them which could be applied on the 30 seconds period. It's a heart rate, standard deviation of heart rate, and RR interval, and standard deviation of RR interval. But for resting state assessment, of course, we use all of these HRV parameters, but none of them were included in the model.
Okay, thank you.
Two questions.
Yes.
One, the way you present the tasks, that means in random. So did you think that if you didn't make this in random, but in a specific way, increasing or decreasing, could influence the results or not?
I suppose that it could be because when I performed it by myself, I did feel some fatigue. Not very much pronounced, but of course a little bit. So of course we organized the session with pauses between, but we just wanted to reveal the influence of the frequency, but not of the rhythm of frequency, because if we started with the 30 beats per minute and ended with the finished with the 180, we could see maybe the fatigue effect because the faster.
Yeah, the second question is, did you check if there were some kind of changings in the modulation of the muscle coordination activation of the muscle, the activation pattern with changing the frequency? I mean, were the muscle in the same way in time and intensity activated? It doesn't matter how was the change in the frequency of the tasks of the sun.
I think not, because we just analyzed the EMG amplitude for the whole session. We did not analyze yet the beginning and the end and the middle. Maybe it will be interesting because the dynamic of this process is also interesting, and maybe it's depends.
I mean, you know, the old question about the degrees of freedom control, no? The Bernstein problem. So if you check it this, but okay, thank you.
No. Okay.
Okay. And if no more questions, thank you, Anastasia. Very interesting presentation. And if no more questions, I will make my short presentations. And now my presentation. Okay. I would like to talk about brain alpha oscillations as my favorite subject for study as a neurobiological marker of posture control. And posture control is the most bright example of sensorimotor integration, where brain acquires, accept the information from different kind of sensor, and after decoding, controls the muscles. And it's different kind of afferentations, role brings to the brain, and brain put the commands to the organs. And it's like in Bernstein's scheme of sensorimotor integration from 1926, that is a process of receiving sensory or affective information, its interpretation and comparison in some comparison device, and in the transcoding, processing of this information in transcoded center, program device, and to receive a command device this information, and produce, execute muscles, make a force, or with some execution instrument movement. And again, this integration is work like a feedback system. So why feedback is the most effective way to control something, in posture control including. And brain plays a role as a podcast. I could not understand why, what does it mean podcast? Now, finally, I understood when I try to understand Bernstein's potential explanation for sensorimotor integration, like a podcast in baseball. And this role of podcast plays thalamocortical, basal ganglia, cortical interrelations. In the brain, basal ganglia and thalamus play a role of peacemakers, and they send information to the motor cortex or other kind of cortex and receive back feedback. And so this system is working as a unique system, feedback system for sensorimotor integration. And the key role of in sensorimotor integration from the beginning of last century, it's known and was proposed by our Russian genius, neuroscience, scientific genius, Michael Livanov, who told that alpha brain activity organizes the connections between different afferent efferent links of the conditioned reflexes. And Nikolai Bernstein, he, in the beginning of last century, proposed that alpha activity organizes the correction of movements due to rhythmic fluctuations in the excitability of the elements of systems that control movement. So our hypothesis is that alpha and posture control have interrelations, have no too much evidences from literature. As you see, till the last time, it was not almost investigated. Moreover, despite that investigated a little bit, nobody have common interpretation of alpha activity. What does it mean? Mostly just think that alpha activity means the amplitude in some standard range only. Meanwhile, physical assessment of electrical potential means that not only amplitude, but frequency, very important. And Russian investigator, researcher Vladimir Pravdich-Neminsky, who lived in the beginning of last century, he showed its picture from his publication in 1913, before Gansberger, that electrical activity of the brain decreased in amplitude when eyes open. And he proposed that brain activity, electrical activity means changing the amplitude and frequency. It doesn't mean waves activity. So when we will talk about alpha activity, we will talk about the next signs. First indicator is decreasing the amplitude in response to eyes open. Eyes open, big amplitude, decreasing amplitude in eyes open. Second, on the spectrum, it's amount of alpha suppression. Second indicator is the frequency and the phenotypic indicator. Frequency of the amplitude peak in rest in posterior areas. Individual alpha peak frequency. And third one is spindle-like form, that very informative sign of alpha activity. And from the other side, stability assessment provided with the help mostly with standard deviation of center of pressure displacement, or mean of speed, or mean of power frequency, but as shown by many investigators and researchers, the entropy, sample entropy, and energetic parameter of displacement of center of pressure is the most informative parameter for measurement, posture control, and stability. So the question of my research of review was what alpha activity indices can characterize various mechanisms of posture control. What is the interrelationship? And as we remember, the one of type of the most important type of afferentation and mechanisms for posture control is visual afferentation. It's well-known Romberg balance test, and it has relations when our eyes closed, the alpha power is big, but our stability is very low. As you see, center of pressure displacement is wide. And in eyes open, decreased activated brain and alpha decreased, and center of pressure displacement decreased too, stability increased. But when we imagine, and there is negative correlation between alpha activation and center of pressure depression. So not so easy interrelations between alpha and posture control. Moreover, activation or decrease in alpha amplitude is not a unitary phenomenon. Different frequency bands show very distinct type of reactivity. For example, in alpha, in low alpha, lower than individual alpha peak frequency, activation associated with general involuntary needs for attention in unconscious condition, and activation in upper alpha frequency shows a clear connection with the requirements of cognitive processing and control. So, very interesting investigation of Napalkov from Moscow State University and his team. He showed that non-skilled marksmen showed decreasing alpha in alpha amplitude, in alpha 2, higher alpha frequency, in response to eyes open, and more lower alpha amplitude during the executive movements. But and again, alpha stability increased with eyes open, but stability decreased in spite alpha was decreased in non-skilled marksmen and students. And in skilled marksmen, opposite, in eyes open condition, yes, stability decreased, but alpha increased, alpha 2 increased in amplitude in spite the stability increased too. It is happened only such paradoxical increase of alpha amplitude and postural stability during the aiming and marksman only is skilled marksman. About what it's talking that alpha 2 is a sign of cognitive control of and automatic performance. Moreover, it was shown with summer and posture that speed of alpha band or frequency of alpha band oscillation predicts the temporary resolutions of visual perception. So in subject with fast alpha, they recognize two flashes versus subject with slow alpha, who recognize just one flash. And it's not surprising for me because it was shown that increasing frequency of alpha waves, as Anastasia now showed us, uh, reflects the optimization of psychomotor performance. So frequency increases in self-control enhancement condition and frequency decreases in unconscious conditions. Alpha amplitude doesn't change. And it was interesting that providing just only kinesthetic or only vestibular information could lead to incongruence effect and consequently higher alpha suppression, reflecting increased cognitive demands. In opposite, when it was possible to control and more automatic. And the most interesting from my point of view results about support of orientation, role of support of orientation in postural control. It was shown many investigations that during the evolution, upright posture lead to the transformation of lower limbs and caused a highly specialized human foot. Yes. And as a result, foot has lost its gripping function and has become a single powerful lever, like in investigation of Renzo and Henrietta. And this powerful lever began play a key role in support of orientation and so optimization of posture control. And straightness made it possible to free the upper limbs and turn them into organ of labor and hands of which become capable to precise and gripping and complex labor activity and playing piano, playing violin. As a result of human participation in labor activity, there was an urgent need to solve and plan tasks which caused the development of cerebral cortex, which caused the development and increased nerve number and nerve cells and change their locations and increase a number of network attachments. So it was shown with our investigations and other researchers that musicality, virtuosity, and sound quality increased in people who were standing versus to sitting. So supportive orientation, increasing training of supportive orientation can increase the quality of musical performance for violinists. And if we compare how change alpha, and not only alpha but EMG2, EMG of forehead muscles, not participated in performance. We see that in sitting position, alpha 1 decreased, alpha 2 decreased, and EMG increased, while in standing position, alpha increased, opposite to EMG that decreased. So it told us about the optimization with support of orientation. Moreover, instructions how to increase alpha 2 for improving cognitive performance during the neurofeedback training. We use data of Codwell, Slobunov, Kozlovsky, and others that when subjects bring their body weight onto their feet, that resulted in increases alpha 2 power. And training of transferring weight to the forefoot could bring to increasing alpha 2 power. And really, we have shown that change in position from sitting to standing in women who trained Aikido with increasing support of orientation, increased alpha power, alpha 2 power, and spindle length, especially spindle length as a sign of optimization psychomotor performance, was increased only in women who trained Aikido with the training of this soul, this part of soul, support of orientation. Interesting result we received after stabilometric biofeedback training for stability, that those who reach success, their individual alpha peak frequency increased. And again, we can talk about that alpha peak frequency could predict success in training, because alpha waves are results of local cortical network tuning, which depend on genetically determined calcium T-channel activity. The second reason is that alpha waves are those oscillations that underlie the dominant hereditary determined brain frequency. And alpha waves dominant frequency from posterior brain area is reproduced in eyes closed rest conditions, and so could be the phenotypic sign of marker of cognitive strategy. And so in conclusion, I can in conclusion of my review, I can conclude that increasing individual alpha peak frequency, increasing activation in alpha 1 range, but decreasing activation in alpha 2 range, and increasing length and amplitude of alpha spindle could predict efficiency of postural control. So thank you for attention. Okay. Okay, we have less than 2 hours, so I think that, Murat, you can restrict those places that we don't need to be, or maybe they will download all our symposium. On some questions, maybe.
Yeah, actually, I have 1 or 2 questions. That was very interesting for me because, as you know, I'm from sports faculty. So as I understand from your presentation, if anyone trains the biomotor feature balance, probably his or her alpha 2 activity will increase.
Yes, not just maybe activity, amplitude.
Amplitude. Okay.
Activation decreased, but amplitude increased.
Okay. And maybe this is a question for you directly, actually. If can we assess if the person is a pro in his or her branch, let's say he is a marksman. If we measure only alpha activity, can we classify him or her as a pro or amateur in different branches too?
You know, it's very interesting question, and this question was for researcher in previous century also. And Klimisch and Vogel and a lot of other researchers, so they showed that because alpha frequency is an individual heredity determined index of brain activity, it's possible to, and we had shown that those people, those subjects who had a higher alpha frequency, they are more successful in memory demands, in some execution demands and motor demands, in comparison with persons with low alpha peak frequency, lower than 10 hertz, for example. And those people who had a lower alpha peak frequency, they had other cognitive strategy like originality and more creative thinking, for example, sometimes. But it's general.
But
In
maybe
intra-subject
for the cyclic
variability.
sports, it doesn't work because the cyclic sports do not need no originality, no creativity. So I think it depends on the kind of sports.
Oh, exactly. For sports, yes.
Mhm.
I
Yes,
dreamed
yes.
of a piano playing.
Richter, maybe you remember such pianist like Richter, who put out his royale before playing to put his weight on the and some violinists who the vibration.
Yes.
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 About the vibration with
No,
for violinists.
vibration on the supporting surface, for instance, for foods. Which kind of influence did you investigate this? You know, there are these vibration plates, and that could make.
Vibration of plates.
Yes.
Force plates.
Force plate.
We did not, as far as me, we didn't investigate it, but was one slide I demonstrated. If you would like, I can show you. One slide of not my investigation was shown that when only vestibular or only kinesthetic afferentation received the brain, the more activation in whole alpha range.
Okay, thank you.
No automatic. Automatic posture control with support afferentation, without vestibular afferentation, additional vestibular afferentation, decreased activation. It's very interesting paradoxal effects. Again, paradoxal effects.